Welcome to today's talk. My name's Phil Mazanet, and I work at OctoML. At OctoML, we'd work with customers to get models into production. In today's talk, what I want to talk to you guys about is, with all that information from customers that we see about models going into production, what are some of the mistakes that we see that people continue to go through, and how you can avoid those mistakes so you can get your models to work much faster and actually generate some revenue. Generally, what we see when we're talking to customers is that customers are trying to get the models into production in whichever way they can. So they're brute forcing these deployments by passing a lot of different frameworks or creating specific, very rigid pipelines when it comes to getting those models into production. This, of course, creates a lot of mess when you have to introduce a new model, when you have to go in and work with different new frameworks or anything that basically goes outside of what was already created. Generally, what also gets cost as a result of this is folks are basically passing on repos that contain the environments that they have in their current scenarios, in the ways that they're training these models. When that happens, a lot of the nuanced information that needs to be known about how the model gets deployed gets lost in translation. And it becomes very difficult for the folks that are actually deploying these models to do it in a very efficient way. That, of course, causes project failures and delays, which is one of the main reasons that a lot of these models don't make it into production fairly quickly. That, as a result, also causes a number of folks to then have time in their hands in inappropriate ways. And by that meaning, people are essentially going out there and doing a lot of trial and error when it comes to rebuilding the environments that are necessary to actually build the models and deploy them into production. And then for anybody else that is downstream from that, it causes a lot of sideline or a lot of waiting and basically misuse of the time that you could be doing to deploy further models. So this brings us to a point that if you look at some of the information that VentureBeat put out in 2019, that 87% of the models that are actually trained and that folks are working on actually never make it to production. This is, if you actually think about it, that means 13% of the models that are actually being worked on make it to production, which is actually a really low number. If you think about that and think about that each of those models takes about a quarter of a year to actually get to production, it means that there's a tremendous amount of waste that's actually happening, because no matter what, models, before they get to deployment, still have to be trained, that still have to consume some data. There still has to be a lot of investment people-wise in a number of different other things that go into building a model. And so if we really take a second and stop thinking about what this actually means, it means that we're actually generating a lot of work that is not returning any value for enterprises. So let's talk about some of the mistakes that we've seen customers do when it comes to actually deploying models. And there's definitely a lot of learnings that we got in from talking to a bunch of different customers in our company. The number one mistake that we've seen is around not taking into account the end state hardware target where the model is going. What I mean by that is models are typically trained in environments that are very large, that are distributed, that enable the use of clouds, for example, like the Azure ML Studio, and use of GPUs like an NVIDIA GPU. And then not taking into account that this needs to go into a bunch of different environments. Sometimes those environments cannot be selected. So for example, you may have to deploy in Intel CPUs or AMD CPUs versus the NVIDIA GPU that you thought that you were building the model for. And there's also a component where somebody has to figure out what is really the most cost-effective way to deploy this model. Sometimes that decision actually alone dictates where the model is going to go. And this is not even incorporating something, for example, like if I need to deploy the model into an edge device, what happens with that particular state? The edge device may actually not be able to run the model at all because it doesn't have the necessary power. So this is a problem that we see people usually having to deal with quite a bit. And some of the things that we've seen in order to fix this problem, or some of the solutions that we've seen customers take, are doing things, for example, like exploring quantization or pruning or other techniques that, of course, change data types to be able to achieve a smaller model, something that is much easier to consume for a lot of devices at a cheaper cost in terms of the actual running. However, that, of course, means that some of the accuracy of the model can go away. If you're changing data types, if you're changing the precision of the model, that could mean that the model is no longer valid. So there's obviously something to think about there. Another way to solve this problem that we've seen from customers is really just throwing more compute at the problem. That's obviously a really good solution up until a point, of course, because if you think about it, as more compute exists, people are building more complex models. When people build more complex models, they require more compute, and the circle continues to go on. And essentially gets to a point where it's not even functional or useful to be able to run these models at any point in time because they're just so costly to run. And we're starting to see that with some of the larger natural language models where they're just getting really, really big. And these are models that are not going to run outside of data centers. The last thing you can do, or we've seen customers actually do, is optimizing the model in a different way. So not using things like quantization and pruning, but actually looking to see how you can use the stack of the machines that the model is running at. And by stack, I mean software stack. So for example, using the CUDA libraries appropriately, using the Intel DNN libraries, or using even better ways to compile the model for the instruction set of the particular hardware target. There are companies that can do that for you in terms of an actual automated process, and there are solutions that are used by those companies. For example, TBM was a project that was created from open source to be able to approach this particular problem, which is essentially replacing the tuning of the model that is done in a hand-tuning way by using machine learning for it. OctoML just happens to be a company, which is a company I work at, which utilizes TBM as the solution for that. Now, there are other solutions you can use. So you can use other technologies like TensorRT and Onyx Runtime that do similar approaches. Now that we covered that, there's another problem that we keep seeing with our customers, and it's a little bit different than the problem that we just talked about a second ago. This problem is less related to the cost and the performance that you have to think about when you're actually running the model, and it's more related to the options that you have when you're thinking about deploying the model. And what I mean by that is, obviously in the training space, there's a lot of room for possibilities. So, folks have access to things like Hugging Face and all these different libraries that are coming out that make model creation much simpler. And you're able to basically leverage the knowledge of many, many people that have built these different frameworks for you. The problem with those is that those particular frameworks have requirements that are very specific to the type of machines that they've been compiled for. So, of course, if you're taking a model that has been created with PyTorch with some new library, and you want to put that into a Kubernetes cluster, say that has an NVIDIA GPU and one that has an Intel CPU, then you're probably fine. However, let's say that your actual product needs to run on a phone or on an edge device, and those different devices have versions of an OS or have different types of chips that are not supported by a Docker approach, then now you have to start thinking about how do I generate assets from the original model that can run in an efficient way in that particular device. And so some of the things that people are doing is, of course, doing conversions to things like TF-Lite, which is what you see here. But if you take a look very closely in the diagram, that means that you essentially have to create a completely different approach to deploying this model. So now you basically have to maintain different pipelines. And that, of course, causes a ton of stress on the organization. Now, there's two ways that we've seen customers address this particular issue. And the first way is which essentially I just talked about, which is customers are basically going in and saying, okay, we have a number of different frameworks and different devices that are important for us as an organization. So we'll go ahead and build pipelines around those. We'll put some guardrails and limitations, but it'll allow us to do an automated ongoing process. Now, the problem with that, of course, is that if you do that, you're essentially limited by whatever the pipelines can do for you. The minute that you have to use a new framework or that something changes within the framework or something changes within the device, you have to start creating a new pipeline or a new workflow. Most likely you can't get rid of the old one and you have to basically maintain a new one and continuing to add these number of pipelines that you have to support. Another option, which is a much better option for this type of problem, is to essentially look at how you can recompile the model for the target and for the actual stack of the target where the model is going to run. What I mean by that is instead of thinking, how do I package all the different dependencies that I need to run this model, let's actually convert this model into something more universal that can actually run in all these different devices and take advantage of the devices that or the instructions and the accelerations that devices provide. There are ways to do it. The way that we're tackling it mostly in our company is using a container approach. There's also ways that you can do it with shipping C libraries and so on. That being said, this allows the organization to have a much more fluid way to look at deployment and basically have a translation layer that allows you to always develop models in whatever frameworks you have without worrying about how they need to run in the end state. So the third mistake that we see is actually more of a culmination of everything that we've seen. And it's really, I would say, kind of the most impactful problem that we see in deployment. And that is this concept of there is a wall and there's something that you have to throw as a machine learning researcher, your model that you've built and everything around that model into, let's call it a Git repo and a Jira ticket, and then assume that somebody will be able to pick that up and actually rebuild your model. That is very common in many workplaces and many enterprises. And the problem with that is that essentially you're putting a lot of work on the folks that are going to deploy the model, whether they're infrastructure or some other team, to actually go in there and understand what it is that you did as an ML researcher when it comes to building this model and getting the model to be as accurate as you want it to be. Some of the things that those folks have to do are things like, for example, building the environment, making sure the right Python packages are there to actually run the code the way it's supposed to be running. Other things that may have to do is clean up your code, so make sure that the code is efficient and it's not crashing and it's not running out of memory or things like that. If we really think about, and I mentioned this before, if we really think about mission critical workloads, some of those folks may actually have to take a look back at the entirety of the code and think about how they translate it to a better language. So for example, get away from Python and use something like C. C is a much more dependable language. It's something that you probably want to run in something that needs to make sure that is mission critical. But the problem with that, of course, means that these people that are actually doing that recompilation or translation in C have to fully understand what's actually happening with the model and have to fully understand the mathematical properties of the model so that they can translate it to that particular piece of C code. On top of that, those people actually have to understand the stacks that are necessary to run in those particular machines and how you can get those accelerated. For example, they need to be CUDA experts, or they need to be VNNI experts, or whatever is the library of interest. Of course, that's a very complicated set of folks to find. So if we really think about, those are huge problems that essentially the research team is putting on to the infrastructure team by just throwing the model over the wall. The way that we like to think about it, and we've been talking to customers about how to fix this, is that you essentially have to remove this concept of the wall out of the equation. And think of models as something that is much closer to functions in a software program. So something that you can, essentially something that you train to make some decisions based on some data, which we all know what that models are, and then treat them as a function like any other piece of software. By doing that, you can essentially start inserting yourself earlier into the process of the DevOps or software development process. And that way you can essentially start informing some of the folks that are working alongside you on what are the things they need to be thinking about. So for example, with software developers, you can provide them quicker access to a prototype of the model that you're actually working on. They'll be able to actually work with that model, test something, even if it's an early version of the model, and be able to actually start building the app the right way. From the infrastructure point of view, these folks are also going to be able to understand what are the resource requirements of this model so that they can very quickly advise if the model is or is not going to be able to run in the targets or the hardware that you intend to run the actual model. For example, this would solve something like, hey, your model doesn't run on a Raspberry Pi or whatever is of interest. If we do this in a much more iterative way, in a much more connected way, that would essentially enable us to really take advantage of all the stuff that we learned when it comes to agile software development and bring that over to the model space. And by doing so, we can essentially get models faster out the door. We can break down this whole concept of only 13% of the models are making it to production. And we're able to get a much, much better cycle of reproducibility and iteration when it comes to rebuilding the next version of the model and so on. So I hope that was a helpful point to start talking about ways that we can really get models into production faster. and what else we can do to avoid these mistakes. Thank you so much for taking the time to go through this presentation with me. And if you do have any questions, please feel free to reach out to me at any point in time.